So let's go to our today's topic. Our today's topic will be a bridge between what we have seen so far. So far we have been talking about quite static systems. We always said, like, we measure temperature, we measure pressure. We might repeat this experiment, and kinda it was always the case that that this was happening in sort of a steady state. Basically, we were trying to build some static models, estimate some constant, so something like a steady state of some signal of some process. And well, you have seen it in your exercises. Yeah, the latest exercise, the distillation column. Basically, you were given the data, which were almost the steady states, if not really the steady states. And the subject of identification is more about the dynamic system. So far we have seen more statistics, applied statistics. Somebody might already call it machine learning or anything, applied statistics, but to let's say static systems. And but you are already well aware, for example, in your theory of automatic control. Now you are studying the discrete time systems. Is that right? Okay, good. So we should today aim to make a bridge between the static identification, static data analysis, and the dynamic systems. And this bridge is called filtration. Yeah, what's the subject of filtration? Rumors say that at your course, technical means of automation, you have been doing some filtration. What is the message learned? What stick in your mind from the filtration topic? We can reduce the noise. That's one of the possibilities. How there usually came some adjective like this sort of filter or this sort of filter, and one type of that filter was the one which was reducing the noise.
I can say that in Slovak, dolno prepustný RC filter.
Yeah, low pass filter, exactly. Yeah, low pass filter was the one. Why was it called low pass? Or well, the equivalent in Slovak, dolno priepustný. Mm-hmm. Mm-hmm. Okay, good. Low pass. Low pass. Yeah. Good. Why low pass? What would the so pass is I let go something which is low, or I make it's the Lord of the Rings, you shall not pass. So what will pass is something which is low. What does it mean, this low? What does it refer to? Exactly. Yeah. So and low frequency means what in the let's say in the time domain? Let's say that I have some.
Well, I'm not sure if I answered the right question.
Let's try.
We got the signal. We can use for transformation to like change and there's like with different frequencies, and we just remove those with high frequencies.
Exactly, exactly. Yeah. So just some sketch of a signal. Later, I have even a better plot. But as Adam says, this signal can be basically decomposed into two components. Let's say this will be the high frequency. So the one which we see is changing quite a lot, almost periodically. And the other one, which is basically this trend that we observe in the data. So our it's of course not plotted to scale, but if we have our original black signal, then the low-pass filter should ideally return us this signal and leave the noise which is in the signal apart. So this will be the ideal low-pass filter. Of course, if this is the output of the low-pass filter, then what would this be? This will be the output of the high-pass filter. So the high-pass filter should basically what? Tell us how in the first level of thought you can say, okay, it can tell us how big is the noise in our signal, or it can also tell us when the signal might change. Okay, before going completely into the filter domain, these signals, let's first have some little word about the filtering in the static case. It does not seem reasonable that we say we are talking about the filtration of dynamic signals. Yeah, get some working chair, Jakub. The one there should be looks fine. Test it. So let's say that we have data, that we collected some data from an experiment in the form of time series. Yeah, the time series, let's say temperature, pressure, and let's say we plot one of the signals that we got, and we see something like this. What's the problem? What happened here? Yeah, there is some suspicious value that we might that we would call outlier, and well, what to do with it? We saw it. To remove it. What does it what does it mean to remove it? One possibility is that, okay, I cut out. No, that should have been red. That I cut out like this portion of the data. Mm-hmm. Mm-hmm. Okay, so remove and replace. In the that's a question whether we should do the replacement. Removal, yes, but well, if we are interested in just steady state model, well, we might say, okay, I have some other data points that might, or other signals that I measure that might look I don't know, perfectly normal, even in the same window. I can just say yes. I just remove all of these, well, because I still want to keep the track on what happened in the first part in the data. It's well aligned with between signals 1 and 2. What happens after this outlier? So I can and the remove and replace would then do something like this. It's already questionable now. And something like this would mean either what Adam, you were suggesting that we just copy the past data here, or
I would prefer to use a mean, for example, from last 100 measurements.
Ah, okay. So just in the past, yeah?
Yeah.
Okay. Okay.
Or also we can extrapolate somehow, but
What does it mean, extrapolate?
we can somehow predict how it may be.
Predict.
Or interpolate.
I mean, we have all these data, so it's not so this everything is the past. Yeah, we already collected the data, and now we are 1 year after collection of the data, and we are just processing it. So
I would probably use the first value in front of it and behind it, and just
so last good value and first good value after the last good value before the outlier, and the first good value after the outlier, and make some sort of average. Now, if we, for example, in this situation would take some average of the past values, this signal might be good. I mean, well, we didn't zoom in how exactly it behaves, but here it might be already problematic that we basically, since we want to keep the data aligned, we got rid of the possibly good data. So even our replacement should be somehow in that range. Yeah. So this sort of and there are tons of the things you can do, and you will be doing based on what you expect from the reality, how the system behaves. So this all here is still sort of based on the, let's say, one-dimensional observation. Yeah, how we went about it. We looked at one variable, we spotted some outlier. How can we spot the outlier, let's say, automatically, like without the plotting? Yeah, because I mean, plotting, if we have 10,000 signals, is not the most fun work to do. So with the how can we spot them?
Maybe sudden change of gradient or derivation
of the derivative.
Or we can say that, let's say we have some value, and the next one can be within some zone or something.
Yeah, good suggestions. So what Jakub says, we will be sensitive to the change of the signal. We have to be aware that this signal will have some noise, and this will intervene. Yeah. Not saying this is anything problematic, but we should be aware, and this is where some well-tuned high-pass filter can help us. I'll show you an example in a second. So in a well-tuned high-pass filter, we would get the information about the noise, but when the signal changes abruptly, changes a lot, its derivative is higher than usual, then we should also get this information. And so how do we detect this? So detection, rate of change of the signal. That's the Jakub's approach, but beware the noise. So we need some sort of a filtering, and what Adam says is what, that we find some long-term limits of the signal, which are acceptable, and beyond these limits we have unacceptable values. Okay.
Otherwise, you can say or use the saturation for the signal somehow. So even if
What?
Yeah. Or something, we can somehow block it, so it won't reach.
Okay. Well, so let's first do the detection, because what you are saying is already how you remedy what you do, how you process the signal. So, but we can detect, let's say, out of limits, whether the signal is out of the limits. But okay, that's a very interesting point. So let's say we have some limits on the signal. And we can also we can easily then find out, yeah, this will be this outlier will also be detected by this sort of a limit-based detector. How do we get these limits? That's that might be the case.
Or we can use the mean for the of the data, and say we can define it's plus minus some value.
Yeah. What could that value be? Sure, I'm not asking about the exact number, but how would you get that value?
Let's say that, for example,
Standard deviation. Yeah, exactly. So Yeah, we have basically two possibilities, or we can combine them. But either we know physical limits. It doesn't make sense that the temperature in this reactor is at minus 200 Kelvin. Yeah, or we have some statistical limits. Statistical limits. The point is, or the or how we can approach the problem. The definition of outlier is something which is rare and which does not conform the probability, what our assumptions about the signal. So we can very easily find the mean, find the standard deviation, and then it's up to us to say, okay, our limits are then the mean of the signal minus, and now we can say, let's say 3 sigma of the mean plus minus 3 sigma. Yeah, that's usually applied. What you can of course try to do once, let's say the problem is that if you are doing this originally, the outlier is still in the data. So what happens if you take the outlier into the account? Well, it will shift your mean. It will shift the standard deviation. So also a good practice, like a check, is once you remove this outlier, you do the statistics again. You find the mean, you find the standard deviation. If they do not differ that much, then you would say, okay, the outlier which I removed was really an outlier and didn't infer with my statistics applied. Yeah. What becomes? Yeah. Now we will have some pictures, but let me. So this was sort of a very briefly, like one-dimensional analysis. Basically, we are looking at one signal at a time. We are ignoring that we might have other signals. The same thoughts as we just did can be applied to the multi-dimensional case. What is a simple example? So in the ND case, we might have our traditional example, let's say some temperature and pressure along the time, and these two would be nicely correlating. Maybe I just do it even more extreme. Let's say, it's still not enough. So what if we, let's say there is these bumps somewhere in our data, and if we apply just the one-dimensional statistics, we might say, okay, our pressure has been always within these limits. So this here is an outlier, but of course you are sensing a problem here. There might have been a situation that just our operation of some reactor distillation column and so on went just out of the usual situation. But anyway, when the pressure increased, the temperature increased. So this is not a outlier in the form that something went wrong with our sensor, that we recorded a wrong number in the database. This is just basically saying that there are that something happened, and we can still say that this situation was perfectly normal. Because let's just plot this in our correlation plot. Yeah. So temperature and pressure, how would that look like? We have some, let's say, very usual situation that would be close to the mean of the temperature, close to the mean of the pressure, and our data here, and well, that seems, we have plotted it this way, that there is quite a bunch of the data. Well, they are basically just saying there are some. So let's make this cloud big. So let's say this is our mean situation, and there are some data that are just with the higher temperature, higher pressure than usual, but they are still kind of showing a correlation that we would even expect from the physics, the correlations that are happening in our plant.
We use just like moving mean, like every 10 values, and it's moving and giving mean of all values. Like all the 10 values, but it's like k+1, k+2, and it's moving.
We will use it in the second, but okay. So let's say that we use a moving mean, moving average. What would that mean? That basically this. Oh, sorry. This should have been. We basically get something like this. Yeah. Yeah.
And then the standard deviation would be added or subtracted.
Okay. Mm-hmm.
So it's gonna be copying it.
Okay. I see what you mean. So you good idea. This is really used. I didn't want to go that far, but yes, you can also. So this limits here, they are just basically static. Yeah, they are based on one number. They are just the standard deviation from the beginning of the operation or beginning of our data until the end of the window we are looking at. What Adam says is, okay, let's have some sort of a window where what will be our assumptions, our thoughts behind. We don't care much about what happens. Well, definitely not in the future, but what even happened to the past of the signal. So however the signal was changing, you can maybe see it very nicely here. At this point, well, however this signal was changing, these transient effects, they are over. So the data that we collected in the far past do not influence our present values. And in that way, we can actually calculate. So what would happen if our window is like this? So basically, our mean we will identify based on the black line, and maybe our standard deviation would look like the most of the data points. What would happen, let's say, if we shift it? How to plot this? There are too many lines already. Too many deletions. How do I delete exactly this one? Perfect. What happens if our window was shifted? Somewhere here. So what is the mean here? The mean value is somewhere. I'm missing the good color to plot this. Let's try the yellow one. Yeah, so here is the mean that we would calculate. Yeah, we just take these black values, we calculate mean, average, sum them, divide them by the number of samples, we can calculate the standard deviation. What would happen in this case? The mean is here, and we can directly see that the standard deviation here is just small. The data is very close to the mean, but here the data is far away from the mean. So even our standard deviation, or plus minus 3 sigma, would increase. Hopefully the plot is still kinda readable. And Adam, what to do then?
Also, probably it would change like the standard deviation.
Yes, that's the dotted line. So now it's like this.
Okay, so I think it's okay because we want both data. And if there's some noise or some, I don't know, sudden spike in it, it will still be moved.
Exactly. Yeah. Yeah, so in our previous situation, let's just look at these data points, because here it's already messy with the lines. So in our previous situation, this data point here would be out of these overall historical limits, and we would consider it outlier. Here we already used the moving average. Here we already used the moving average, and that basically makes our previous constant, these green limits, that makes them dynamic. Yeah, they are small when the signal is not changing much. They are larger. They grow up if the signal is changing. Good, very nice observation. This is what is really used in the practice. We will get to the mathematics of the moving average soon. Also, we can use advantage of this correlation plot, because we already know about the correlation matrices. So if we what was our case? How can I go back? What was our case in the last lecture? We have found out that, well, we have looked at the multi-dimensional Gaussian curve, yeah, with the covariance matrix. This is when we were doing the analysis of the parameters that we identify from the linear regression, and using the correlation matrix, the VP and our covariance matrix and our estimate of the parameters, we sort of ended up, or you sort of ended up believing me that all these expressions are equivalent. So the mathematics goes like this. Our uncertain variable, be the parameter here, its deviation from the mean normalized with the covariance matrix will be distributed according to the chi-square distribution. If we take the quantile of this distribution, then we can arrive at this mathematical expression, which if you wanna go deeper, just let me know. But this is nothing else than the equation of an ellipse. Yeah, and as much as we say we wanna find, as much as we say as our confidence will be, then the radius of this ellipse will grow with this statistical parameter. So we can learn either the limits of our parameters, but we can also see the correlation. But come on, we can use exactly the same thing in this situation. We know how to get the covariance matrix. How was it? It was some kind of a average, and we know this matrix notation. So we only need to say if our X transpose V inverse is less or equal some chi-square value, then this will this expression here will be if we plot it, give us the covariance ellipsoid. And what is good about this guy here? Let's say we do it like this. This will be this math here will be basically our testing criterion. It is the same thing as if we before said, if some value of our signal is out of the limits, we discard it, we consider it an outlier. Now we can take, so the X here will be a vector of temperature and pressure, and we can plug each point that we have in our database. We can plug into this expression. If this inequality holds, well, that means that this point will be inside the ellipse, will be inside what our historical data was telling. So even if the points like when the temperature increases, and the pressure increases at the same time, will be perfectly valid. Just compare it with the situation if we just take the rigid limits on both temperature and pressure. Let's say we have a point like this in our database. If you just look at the, let's say, the projection, let's say the values of this of the temperature and pressure at this point, if we just have our rigid limits, yeah, so these dots here, well, we would consider this point to be perfectly normal, right? It's in the range of the temperatures we have seen in the historical data. The pressure is in the range of the values of pressure that we've seen in the historical data. What would it now correspond to? It will correspond to the case we got lower temperature than usual, but we have a high pressure. Yeah, so it would correspond to, it will actually correspond to this sort of a situation. Where is the lowest temperature? Somewhere. So let's say this point will be somewhere here. We have the lowest. Let's not plot it at the limits. We have relatively low temperature, but it might happen that our pressure would still be in its ordinary limits, but will be off of the trend that we would expect. Maybe even do the plotting of this guy a bit more down. Yeah, so this is already beyond just looking at the at some constant narrow limits. It's really trying to guess something from the past historical correlations. About the signal. Sort of okay? Yeah, easy to apply and to test. So let's go to the real dynamic case. We have already discussed quite a lot about these sort of plots, how to arrange them. Now I have to remember what was the original order. Okay. Now I'm getting there. So this is almost like a fairy tale. There was a once innocent, nicely looking signal, which was, let's say, the real temperature happening inside of some reactor. Then there was a bad how is it, antagonist, villain. There was a bad villain coming, and this guy was called noise, and it was poisoning our measurement. Yeah. So let's say this is the original signal. This is the measurement or sensor noise. Measurement noise, and the sad story is that we don't know about any of these, because these two guys will basically combine, and what we can and what we can see is just no, I find out that they didn't combine it well. Okay, let's try it like this. Original signal, I shouldn't even call it a signal, because it's not what we sense. It's the variable that we would have measured with the perfect sensor. The ideal sensor doesn't exist, so we get some measurement noise, and this is actually what we measured. You can see the noise is not that. Also, although the plot looks like, well, there is a lot of going on, well, we can still, even with our bare eye, see that the signal is not completely lost. Yeah, so this is our our measured response. Now our quest will be to use some, so we already discussed the high pass filter. Should return us something like this. Now this picture we can now compare. So this is some real signal I took and I pass it through some filters. On the right is the noise, is the simulated noise that was added to the signal. On the left is some signal that was reconstructed, that passed through the high pass filter. What's your observation? What do you think of this? Is it a good filtering, bad filtering? Bad if we want what?
We want the original information.
What is the original information? What we measured is already a collection of two information at least, because we have the original signal and we have the noise.
Well, I mean original signal.
Of the original signal, okay, but well.
If you want to measure noise, then high pass is good.
Okay, so you are satisfied with the reconstruction of the noise. Is this there? But they are not the same, right? So you are correct if you say it's bad, or if you say, well, we didn't get the perfect information about the noise, and that will of course never happened. The two information were combined, and it's not always easy to distinguish with them. We can of course tune our filters to be more or less good. But what these guys at least trying to do, I'm not sure how much visible is that. It would still bear maybe this point here. Oh, sorry. Good. It would still try to bear. I know this is a bad example. It also happens here. Maybe this one here. Yeah, it's still also. So remember, this signal is already got from the combination of these two. It still would hold some information about the changes of the original signal. Yeah. Good. So that would be for our high pass filter. What about the low pass filter? So low pass filter returned us this. Let's compare it again to the original signal. Let's see what Adam says, that whether he likes it or not. What do you say if you now compare the two images? That's our original signal. This is what we got filtered with some low pass filter. Yeah, it's not the low pass filter. It's whatever we say, whatever we tune. Is good, yeah, but it's not excellent. Yeah, that's what you, yeah. So
Picture on the right is already filtered.
yeah,
Then it's better, not so much.
better than not filtering at all. Yes, yes. So of course, I mean, we can see like, yeah, whenever there is a like spike in the original signal, we can see the spike in the reconstructed signal, but it's also not perfect. Yeah, what is the biggest thing it misses? Where would you say?
Around number 19.
Yeah.
Larger spike.
It seems to be not even this one, but also here. The signal is here. Even the original signal is here changing a lot, and our filter is saying, okay, you cannot change, you cannot pass if you change that fast. Yeah, so that's where we observe this sort of deviations. Okay, good. Oops, no. And now, how does the filter really work? So let's do some mathematics, and let's then transform from the world of some means, averages, to the world of discrete time transfer functions. How does the filter work? How can we, if we are let's say doing simulation in a Simulink, we get one of our, this comes later, we get one of our noisy signals. How can we get our filtered output? What was the let's say we are saturation. That would not, so for what?
For the one at the start.
The low pass is something like RC filter. I don't know electrical engineering. But okay. You have all seen the filters in action, and maybe you don't even realize that. Let me just move this a bit. So how could this look like? Let's say we have some time axis, let's do just one little change of our raw signal. Our little change, wait, let's see, blue will be the raw signal. There's something more bluish. So this is our raw signal in blue. Let's say it will start at 0, and we will only do one little change of it. It will change to the value of 1. Yeah, this is our signal. Now, what should our low pass filter do? What should be the red output, let's say, at this point? Or maybe, let's say, this point, like for longer time, the same. Okay.
Should work like first order system.
Exactly. Yeah. So what should happen here? So what is coming in changed a lot. Doesn't matter how much, but changed. What should the filter do? Should it jump the same? Yeah, because what if this change was just an impulse? We don't want this kind of
Somehow smoothen it up. Probably. Smoothen it up, like make it more smoother.
Yeah, but so what does it make it smooth? Yeah, this is the simplest example. Maybe the simplest would be our original signal is doing this. Yeah, so our output of our
No change.
yeah. So here it shouldn't change. But then if we are here, yeah, Jakub is perfectly correct with the. So this, if this response looks like, well, you have all seen this, right? This is like a step response. What would you say? How would the either continuous, probably continuous is easiest. How would the transfer function of this look like? Whenever, yeah, what's the gain?
So 1.
Everybody sees that the gain is 1. Right? Because what should our filter do? The gain is 1. If the signal is 0, the filter is at 0. If the signal is 1 for a long time, the filter should also converge to the 1. So that's one of the key features of the low pass filter. In the long run, if the signal doesn't change, it should return you the same signal. Yeah. Okay. And the denominator?
Time constant.
Yes.
S plus 1.
Yeah. Exactly. So this is even easier than than any sort of a dynamic system, because well, we have just one parameter to fit, and that is the time constant. So if we just change the time constant, we can make this filter arbitrarily slow or fast, and this would actually say how much we are cutting off, how much frequencies we are letting to pass.
And we use higher order of the system.
Yes. then if you are using higher order, of course you can, because basically any dynamic system works as a filter, because any dynamic system, like you simulated in your the theory of automatic control, the two-tank system, if I change the inlet to the tank, the height of the liquid in the tank does not react immediately. Yeah, that's the same thing as the filter. It doesn't get scared by just one change of the input. It would need to see the consistent change in the input to react that way. And if you are using the higher order, then basically then it's better to really look at the frequency domain, because there you can do magics. Yeah, this is what is used in the audio signal filtering. You can really damp some frequencies, like yeah, there is some noise of one musician, noise of another.
Lower frequencies are damped as well, like really low. For example, if there's somebody's, for example, reconstructing something and the frequency of the sound is really low, so it's removed as well.
Yeah. I'm not an expert on the sound signal filtering, but yeah, these are the principles. Good. So this looks like we are just talking about the theory of automatic control, but how can we make this? How can we see some connection to the statistics? Is there some connection? This is one of my favorite graphs, because it's like I do not need to construct some arbitrary example like what we had above. I'll show you. I already showed you this graph in the very first lecture we had. I like these statistics that got created around our past COVID pandemics, and this is one of them. So the blue line, blue curve, is the original signal. We have some time series here. It does not really matter what these numbers exactly are. What is maybe important is that the granularity is 1 per day. Or in the theory of automatic control, you would say the sampling time or sampling rate is 1 day. What are the values? Is the number of daily PCR cases. PCR was some method of testing for the COVID, and this is what we got as a blue curve. What's the problem with the blue curve? Why is it so spiky? Is it showing really? Does it mean that on one day we got 7,000 new cases of COVID, but the day after there was only 2,000 new cases?
Some accumulation.
Mm-hmm. Because of what? Yes, there is some accumulation. What accumulated? Or
yeah, for example, for COVID, it was weekend, so nobody was tested, and then on Monday everybody goes for the test.
Exactly, yes. So if you wanna check your calendar, whenever you see the big spike, and now you can already start to see. So the big spike is Monday, and it's not a coincidence that whenever in this picture you see the big spikes, they are evenly distributed. Yeah, probably Sunday are then these lowest spikes, because nobody was doing the testing or nobody was reporting. That's even another factor there. Okay, and so we were during the pandemics seeing these blue numbers every day in the news, and when we were about to do some control, so to say whether we are closing down some businesses, some theaters, and so on. We actually didn't look at the blue numbers, but we get this red curve, and this red curve was in this what is it, traffic light, COVID semaphore, COVID traffic light. I don't know how to translate it in English. But the filter which is used here is actually 7-day moving average. That's what already Adam suggested for our filtration, to finding whether some value is whether some value is off its limits. So how does it work? Really, the moving average uses some moving or sliding window. In Slovak we call it klzavý priemer, yes?
Ja mám pocit, že
Nebo to klzavý median?
to bol klzavý median a ono tie dva slovička nie je to isté, nie?
I give you that. The red number is what I got. So, well, I did this in MATLAB. So I used the 7-day moving average. I can try to dig this data back and to see how much it changes with the median.
It's like average is more correct because like median it depends, because the average is actually taking into consideration everybody, like every data we have, and the median is just picking the middle data we have.
Yes, that's a good reasoning about it. Actually, it depends on the assumption of what is the statistics, what is the distribution of the randomness, what is the distribution of the uncertainty. So average, we have already proven it before in this course. So the average corresponds to the standard standard Gaussian probability. There is a Laplacian probability. There we don't use the average.
Also, I've heard also comment, for example, like where it's better to use the median. Let's say, for example, if we are talking about the salaries, the average salary, like there may be a lot of people who gain the minimal salary, for example.
Yeah, because the distribution is not like this.
And the average salary is gonna be like it's gonna look probably much better than the median one.
Exactly. Yeah. So, well, there were some good reasons why they choose the median. I don't know why, but average would work maybe almost the same way. So how would this work mathematically? How can we say, okay, we take a 7-day window. Now give me some yellowish. Yeah, we take some. I don't know whether it's 7 days. Probably it's not 7 days. Yeah, because the 7 days is between two spikes, so kind of hard to select. So we need some window of 7 days. So just like in our previous case, we are about to see what we can we do a transfer function of the 7-day moving average? Let's see. So our y, we can directly know it. How could we calculate? Let's say just like you are using in the theory of automatic control, just like we use until now. So k would mean at the current point in time, what is the value of the red curve? So the value of the red curve, it's what? It's 7 days average. So it's taking 7 values in the past, including or excluding the current value itself. We can decide. So how can we, if the blue signal is again this u, how can we write a formula for the 7-day moving average, or let's say some m-day moving average? M. Yk is the output.
Okay. So
K minus 6. Or
from 1 to n.
1 is here.
So K minus 6.
So we need to take k minus 1, k minus 2. Okay.
Then from 0 to n.
So from 0 to m wouldn't work. 0 to m is m plus 1 values.
Or from k. Then.
No. 0 to m, if m is 3. 0, 1, 2, 3. It's 4 values. And our m is... Yeah, we are not gonna get an average if we are summing m plus 1 values, dividing it by m. So, wow, how do we remedy it? Yeah, basically we can we can decide either we put m minus 1 here, or we use 1 here. So in this case, yeah, we will see what we'll get. So which values of u are we picking? How to write it into this formula? No, there is no y. The blue is u, so we are only getting u and
u k minus e.
I. Yep.
Yeah, I.
Exactly. Yeah. So what did we get now? What sort of a filter? We are at the time point k. Yeah, it's I don't know, Wednesday, 22nd of February 2021, and we are summing what? We are summing from I is equal to 0, so we just k minus 0 is k. So we take the number of cases that just got out today, that were tested today. What is it? Let's say it's, what did I say? It was Wednesday. So it's Wednesday, Tuesday before, Monday before, until the Thursday before. We can also, if just changing these indices, we can also get to the past evaluation, like before we know the today's numbers, which would be like doing a prediction. Yeah, if the number of cases in the 7 days were like this, then we can predict. Yeah, so just to say that there would be a little difference from 1 to m. Yeah. we are not using the current value of our signal. So this is already sort of doing the prediction, the future prediction. Okay, so how can we now turn this into, or how can we turn this into the model of the dynamic system, let's say in the transfer function form? So of course our predictions, let me take the 1 over m inside this sum, uk minus I, and let's just compare it with just slight variation. Yk is equal to I to 1 until, which one I'm taking? 1 until, let's take the 1 until m. Variation. Sorry, I missed. Let's just say that we do not need to really have like this 1 over m the same for each of the summands. We can maybe alternate. Of course, if we say that this B1 is equal to B2 and that is equal to Bm, and if the Bi's will sum to 1, do we get the same formulation? Why?
Because we don't get 1/n.
Let's test. So let's say that m is 7. No, that's too many additions. Let's say m is 3. So we just need B1, B2, and B3 to be equal to each other, and B1 plus B2 plus B3 is equal to 1. What's the only possible solution to this?
They have to be 1/3.
Mm-hmm. Right? So we get 1 over m. If we repeat it with 4, 5, 6, 7, so this sort of a condition for our B's would give us the moving average filter. Everybody okay with that? Okay, so this is the moving average filter. What if we do a slight variation? Yeah, because now we introduce sort of a freedom to our filter. We will keep this condition that the sum of these coefficients will be equal to 1. So sum of bi's will be equal to 1. We will not restrict ourselves with b's being equal to each other, but at least we will say that for good reasons the bi is greater, maybe equal to 0 for all i's. What kind of behavior did we now allow? Of course, the previous case is still inside, but this is now much more liberal, much more free condition. What can be an example? Let's say that our m is equal to 3, so b1 plus b2 plus b3 are equal to 1, but now we can choose the b1, b2, b3 more free. Can give me some example?
So we can put different weight on the different
Mm-hmm.
So it's a weighted moving average.
Exactly. Give me some example. What could the b1, 2, 3?
For example, the middle day would be the most important one, so it will be 0.5, so 1/2, and the other will be only fourth.
Exactly.
1/4.
1/4. Exactly. Yeah. So this formulation seems to be quite interesting. We already got weighted moving average. If we would know that the testing is weighted moving average filter, if we would know that the testing is the most accurate on Thursday, then we can make Thursday to decide about the average, or have higher influence on the average that we got. Okay, and so let's now say this is all nice. So this sort of a model seems to be quite working. This yk is equal sum from I equal to 1 until m bi uk minus 1, and it's got its specific name. It's called, quite surprisingly, finite impulse FIR response. And in shorter, it's called FIR, fear. You can also say FIR is quite common. Can we do? This is the filter that we were trying to find. So if we are about to do its transfer function, you can do it because you already know the discrete time systems, and this is a discrete time system. There is some signal which is shifted backwards in time. So what do we need to get? So this is how you are denoting it in theory of automatic control. And don't worry, this one is quite easy. How can we get there?
We have to do set transformation.
So the left-hand side is what? Z minus 1, and what is the shift that we have? What is this? Z to the power of? So now our shift is expressed in this minus I, yeah? what we can imagine here is this is like -0.
So 0.
Yeah. Maybe you are confused with the notation. So when we say yk, maybe you write something like yt minus what? Some sampling time. No, this is not correct. Sorry.
I mean, usually it's like yk plus 1, so it's like it's similar to derivative, so there will be one z1 times
Z to the power of 1. Okay, so this one is
so
not shifted.
yeah, we were not expecting z power to 0, so
Yeah, yeah.
because it's 1.
Yes, yes. So maybe this is more familiar how it looks like on the right hand side. So we got these bi's and whoops, doing it somehow shorthand. So what is the shift of each u?
So we start from 1, so z power
Oops, sorry.
1. I don't know English. I don't know how to say z power to 1.
Z to the power of 1. Shouldn't they be negative because they are shifted? Okay, good. So it will be z to the power of 1, then z to the power of 2, and in terms of the I,
So there will be summation.
no. I mean, in each of these sum, so I is equal to 1. So we have b1, and uk minus 1. uk minus 1. So we are looking not at the current time k, but to the one time instant before. Yeah. So the equivalent, the shift is then -1. So z to the power of -1. If we increase the iterator in the sum, we have I is equal to 2, then we have uk minus 2, uk minus 2, which corresponds to the z minus 2. Yeah, you are all fine with this operator. It is here to help us, because look, this is very complicated. Now, if I just write z to the power of -1. It's saying the same thing as uk minus this minus this. So it's just z to the power of -1. Maybe then write me in the survey where we are of the automatic control theory. Maybe I'm using here some notation. Okay, so how will our transfer function look like?
The summation is the transfer function.
Yes, exactly. Yeah. Just for the, so we have this. This tablet is wrong when I'm writing on the edge. Yeah. So dy y divided by u. We need to divide the left and right hand side with the z to the power of 0. So we got this sum in our numerator, and we have the 1 in the denominator. So we very easily got into our transfer function. Now a quiz question from the theory of automatic control. How do we find out the gain of this system if we have it in the transfer function form? How is it in the time domain?
We can create the limit.
We usually only substituted s for 0, and
That's in time domain, yes.
easiest way.
Okay.
No, it's right because
We can do the limit.
there was like this limit goes to 0, or something like that.
This is how this z. No, there is times s. Okay. T times s. So yeah. So if we are plugging in the s is equal to 0 to find the steady state, so what would that mean for the z? 1, okay. So we can calculate the gain of the transfer function by just substituting 1 for all the z's, right? So what's our gain? So plug in z is equal to 1, which is the equivalent of s equal to 0 in the time domain. So what's the gain?
Summation of these.
Yes. Easy, right? No, Marek doesn't think so. Yeah, these are friends. These are very nice. Yeah, I get gain just by plugging in the z is equal to 1. Yeah, z is equal to 1. So what we were doing here before, we were just saying that we get a moving average filter, we can now call it. Well, and our gain is 1. What was the gain of a good low-pass filter? Well, it was 1. If we now okay, no, I'm not going into this debate. I wanted to start with something which needs more time, but we will do it next time. So next time we will even make we will break all the rules. We will even break the rule of the sum of b's. It does not have to be equal to 1, and then we can basically represent whatever gain of the system, and we will see we can also represent whatever time constant of the system, whatever order of the system. So that's the teaser for the next time. Any questions to this one?